inverse questions. And the inverse questions, they always try to trick you with your domain. Okay, and that's the key part. And if you're taking anything out of methods this year, I told you that everything sketch, everything visualize, because when you visualize it, you're not going to make that mistake. Okay, so let's go. First things first, we're going to talk about, where was this movie? Cool. Composite functions. If you remember, composite functions, the way I like to describe it at the start was I said a function is a machine. And when you have a composite function, you have a machine within a machine. Okay, so a composite function is when you can see a function within a function. It's kind of like your chain rule. You know, you can have, for example, I can give you, for example, 1 on square root of x. So I can see this as you've got a 1 on x function, which is a rectangular hyperbola, and then within that you have a square root of x function. That's 2 functions within one. Yeah, I could have, let's say, square root of x, and then I cube that. That is a composite function. Yeah, because I've got a square root function within a cube function. Yeah, so a composite function is when you have a function within a function. And the way I described it at the start of year chapter 1 was you think of it as you've got 2 machines. In this case here, you're saying that you're putting your x values, which is your input, you put it into this machine, okay, and you get out, they spit out what we call y values, which is really just your f of x. Yeah, because you put it x into f of x. This is your f of x machine. You put your domain into f of x, and it spits out y values. And then you're going to substitute these y values into the next machine, which is g of x. And that's the definition of what you're saying here is you're saying g of f just basically means I'm substituting f of x into g of x. So this is why these are your y values, which is why the very first property of composite functions, the very first definition of that had to be satisfied before it can exist. Anyone remember what the first property is for composite functions? What was that again? Yeah, and that's what I want. I don't want any of you to memorize this. This is very logical in the sense that if we're asking it, we're simply just saying this machine, before you sub into g of x, let's say g of x says I want to take negative numbers. It wouldn't make sense if you had negative y values to then substitute it into the machine, because it wouldn't work. Because the second machine already said, I won't take any negative values. And it doesn't make sense to then substitute a negative y value in. So that's why they say the range of the previous function, in our case, it's f of x. The range of f needs to be a subset, which means it has to work, or it has to be a part of the second machine. And the second machine will say whatever the domain is. They'll say, I can take negatives, I don't take zeros. Whatever the second machine says, you just got to make sure your y values fit in the x values. That's all you're checking out for. And that's why the first definition has to be true. Because if it said, I won't take any negative values, and then you sub a negative value, of course it doesn't work. Okay? It doesn't matter if it works for the first one, it's the second one that matters. Okay? And that's why they're saying, the range of your first function has to be a part of the domain of the second function. If that works, great. You've got a function going. You've got a machine that works healthy. Yeah? So I try to describe it there, just say the y values of f of x needs to be a part or fit into the domain of the next function. Okay? And so therefore, if we switched it, we said f of g, well then that would now mean before you substitute any values into f of x, so you've got to make sure that the range of g has to be a subset of the domain of f. Okay, so it's the other way around. So that's why I'm saying don't memorize it, understand it. It makes more sense. In this case, I'm saying the range of g needs to be a subset of the domain of f. Okay? Now, once you got that down, then that follows then that there's another property. There's 2 properties to composite functions that I told you that you had to take out. So you got the first one as you're saying, range of f has to be a part of the domain of g. What's the next one? What's another thing that they normally test when it comes to composite functions? One more property that you can take out. So besides this one, what else do you know? Yeah. Because the domains, they have to be the same for f of g and the f. We can then say, in this case, they're just saying that the domain of what you're substituting in is exactly the same as the domain of the result. And if that doesn't make sense, I'm going to describe it down here. It just means the domain of f of x, which is what you're where's my pen again? What you're substituting in. See, this is what I'm saying. I'm just saying the domain of f is exactly the same thing as the domain of g of f. And it's a nice property because they'll ask you, find the domain, find the inverse function, whatnot. You need to know the domain and range in order to solve that. And if you think about it logically, it makes sense, because if I show you in the diagram again here, right over here, let's go back to the very diagram here. I said that you're substituting any x values. So these are all my x values. I'm putting it in. These are my x values, which means domain. What domain? This is the domain of f, which means all the x values that I can put for f. What happens is we already ensured that the very first condition was satisfied. We said that all the y values will fit in here. And so what happens is, whatever x values you chose at the start, whatever the y values come out of it, will fit into the second machine, and therefore the second machine will then spit out a y value. But we're not looking for the y value. These are the range. That's the range. We're asking for the domain. So of course, all the x values I put in at the start is technically all the x values for the second machine. It makes sense because we're asking what x values did I put in? Well, I put x values at the very start, which is just your domain of f. That's why we say the domain of f is the domain of your second function. But that only works if this was true. You see, the domain of f would only work if it was already a part of the range is already a part of the subset of the domain of g. If it is, then yeah, of course, every x value that you choose that works, that is the x values you're choosing for the function, the composite function. That's why it is called domain of f is the domain of a composite, because the domain just means x values. So if I said I chose a 1, I chose 1, that's my domain. I chose 1, I put into the first machine, and effectively that 1 is still moving around the machine and it goes into the second machine. So if you ask, well, what x values did you put into the second machine? I put a 1. That's what I did. I put a 1 into the machine. So if you think about it graphically, this is what I'm doing. This is f of x. I've got an x equals 1. I put into f of x, so it becomes f of 1. And then you sub this f of 1 into g of x. So this, effectively, still is x equals 1. So it makes sense. So from the machine, I took an x equals 1, I put it into f of 1, that's still a 1. And then it goes into g of x. Yeah, it's g of f, but still, that is still an x equals 1. So of course, my domain of f of g, or g of f, is exactly the same thing as the domain of f. Because I haven't changed the 1. The 1 has gone through nicely. If you think of it like a pinball machine, or think of it your vending machine, you got a coin. I put the coin in, and I put a 20-cent coin, doesn't matter where it goes. At the end of the day, I put a 20-cent coin in. So the domain, which is your 20 cents, of your first machine, no matter where it goes, I don't care where it spins, it comes out as a 20 cents. So of course my domain for the first machine and the domain for the second machine is the same coin. It is 20 cents, 20 cents. That's why we say the domain of f is the same as the domain of g of f. Okay, if that makes any sense to you, yeah? Otherwise, memorize it, okay? Now, so that's your composite functions. And then the next part I said inverse functions. If you had to take out of chapter 1, I said there's only one property that you had to understand, that you had to demonstrate in the exams, that they test over and over and over. What is that one property again? I keep harping about the one property for inverse functions. What do you have to know? What do you have to demonstrate? Yeah, literally. I'm glad that you guys can repeat that to me. It means that I've drilled in your head that every time you see an inverse function, they're testing if you have the one condition it needs to work is it has to be a one-to-one. That's all they're trying to check. And so once you've got a one-to-one function, actually just to check, how do you test for a one-to-one function? What do you do? Which line test? Is vertical or horizontal? Vertical is for what though, specifically? What does it tell you? If it crosses once, it tells you whether it's a function or not. Okay, but I'm not looking for just whether it's a function. I ask, how do you know if it's a one-to-one? Well, you do both. You know it's a function, and then you do a horizontal to know if it's a 1x to a 1y value. Because if you did just, because you could have this function, is what I'm saying. You could have, I'm just thinking, could you have, if you had this and you did a horizontal line test, it only tells you it's a 1, but it doesn't tell you it's a 1-to-1. So you're right, you do have to do both, but the second one tells you it's a function. Okay, so the vertical line tells you it's a function, and then within the function, you only got two types of function. You got a many-to-one or a one-to-one. That's what the horizontal line test does. Okay, but all right, so we got a one-to-one, and we know it has to be a one-to-one, and then these are little properties that you would have known. The first notation here, it might look funny and whatnot. All that is saying is to find your inverse function, you switch the x and y's. Okay, that's all it means, and that notation just means switch your x and y's, and therefore your second part, once you switch to the x and y's, then naturally it also means that by swapping the x and y's, your domain becomes your range, and your range becomes your domain. Okay? And so therefore, the only one thing I know, if I had to tell you to focus for chapter 1, if you wanted to be sure ready for your exam, the one thing I'd tell you is inverse function is going to come up. That's definite. Every year it's come up, and it's always going to be in your multiple choice. And the one thing that they will try to get you is the restriction of the domain. And it's very likely that they're going to give you something like that. It's a negative linear graph, and the reason why they do that is because a lot of students visualize, they think the endpoints tells you the range or the domain, and you will get it wrong because it's coming down. Or the alternative is they give you a quadratic of that sort. So that way, if you sub in the endpoints, you'll lose out on the minimum. Okay, so that's what I want. That's why I'm saying to you, I want, when it comes to inverse functions, for you to visualize it. I don't care how proficient you are, sketch it, just to make sure that you just don't screw it up. Because it's such an easy question, it's not worthwhile losing a mark on. Okay, and time and time again, every time I give a test, I always find there's going to be someone who will make that mistake. They'll just submit the endpoints, and they go, that's my range. Sketch the picture, and then answer the question. It's so easy, just quickly sketch it. A straight line equation, a parabola, you can all do that immediately. Okay, you can type in your calculator as well. But I do want you to visualize it before you answer the question. Okay, because that's all they ever do. VCA has consistently all they do is just change the domains and the graph, and they make sure that one of it is not at the endpoints. You have to picture it. If you picture it, it makes sense. Okay, so that's one thing I want you to take out of that for inverse functions. Be careful with the domain. It's a very common one that comes up. All right. Now, so we've just recapped on composite functions. We've recapped on inverse functions. Now let's talk about, actually we'll do that later. We'll come back to that. Today's session, strictly increasing and strictly decreasing. What does that mean? By definition, it just simply means, and I've wrote here, f of x2 is greater than f of x1. All I'm really trying to say there is that for every y value, as you move along the x-axis, for every y value, it is always bigger than the previous. That is strictly increasing. Okay, yes? Yes, I needed to state that too. So I just wrote as x increases. But yes, so another condition just to add x2 is greater than x1. Okay, and all I'm just trying to say there is that no matter which x values I choose, as long as I choose x being larger than x1 or larger than the previous one, I just want to make sure, how do I go back? Here we go. I just want to make sure that the y value of your second one is always larger than the previous one. That's increasing. Okay, it doesn't matter what the gradient is. The point is, if x2 is larger than x1, and then the y2 has to be larger than y1, that is technically increasing. There is no point, at no certain point on the graph where it is less than the previous point. Okay, and that's what I try to emphasize here, that it is less than the previous point. Okay, less than the previous point. It will never be less than the previous point. It's always greater than the previous point. Then yes, it is strictly increasing. A typical example will be a straight line equation. A straight line equation will always have increasing y values for increasing x values. Okay, and by the same nature, you can also talk about strictly decreasing. Strictly decreasing is the other way around. Just means that as x increases, your y values decrease. Okay, and that's strictly decreasing. Now, the only one thing I wanted to add onto this is that it says strictly increasing is a one-to-one function, and it is strictly decreasing, it's still a one-to-one function. And same thing, increasing, decreasing. Yeah? Now, the one thing I want you to take out of this, just because we've never really emphasized this, the next one is, if it's strictly increasing and it's a one-to-one, then it also means that your inverse is also going to be a strictly increasing. Okay, so if it's strictly increasing for the function, then it is also strictly increasing for the second, which is your inverse. And if you think about it logically, it doesn't matter which graph you do. Take a straight line equation. If you did the inverse of that, it'd still be increasing. If you take the quadratic graph but restrict it, if you restrict it to just the first half, 0 to infinity, and you did the inverse of that, okay, that's the inverse graph that is positive as well, and that is also increasing. They're all increasing. Okay, so it makes sense in what they're saying, that the function, if it's strictly increasing, the inverse function is also increasing. Okay, now that's all I really had to teach you there in terms of just revising inverse functions, revising composite functions, revising what strictly increasing and decreasing means. Now for this example, I'm going to do the first one and then you do the second one, and that will be it for this session. If the internet goes up, then I'll upload the past exam question I have here. Otherwise I'm going to project it and you guys can have a go with these questions. Okay, but here we go. First one. This is just the example from your textbook, so you can always refer to it. But just in case you've forgotten how to do inverse functions, I'm going to describe it. So it says, for each of the function f, find the inverse function and state whether f, which is the function, and inverse are strictly increasing or decreasing or neither. Okay? So if I have to look at this function, you've got r plus union 0. That tells you your domain already. That's your domain of f. So you know that's the range of your inverse. You've got x equals x to the power of 2/3. Now what I taught you was power functions. I'm hoping at this point you can already picture what this graph looks like. Okay, and just in case you can't, I try to rewrite it for you to see. You're really just saying x to the power of a third, which is cube root, and then you square that. And remember I said when you square things, all the negative values become positive. So you should already see symmetry. There should be a symmetrical picture in your head right now. If you still can't picture this, think about cube rooting. You can cube root 8, you can cube root -8. You get -2 and 2. Yeah? If I had to draw it for you, this is what a cube root graph would look like. So if I squared that, then naturally, if I squared this, all the y values get squared, and it's symmetrical. So that's my graph, but they said that the domain is r plus union 0. So that means I don't have this side. I've only got that part of the graph. Which makes sense, because remember, inverse function doesn't occur unless it's a 1-to-1. So of course they had to restrict this graph. So if that's my 1-to-1 function, that's the blue graph, that's what it looks like, then now you can answer the question. Just by looking at that, it's a 1-to-1. Is that strictly increasing or strictly decreasing, or neither? Yeah, strictly increasing. Okay, so we can tell that every x value, as we go along the x-axis, the y values are increasing. So it makes sense. And all you have to do was find the inverse function. If you forgot, swap the x and y's. That's what I did. Now, if you have troubles at this point here. This is index laws. And if you've forgotten, it's the same thing as your fractions. If you don't like a denominator, it times by 3. But because this is the power, then you want to do this cube both sides, and you get x cubed, and it removes the 3. If you don't understand what I'm saying there, I'm just saying cube and cube both sides. Why? Because remember, index laws means that you can do 2/3 times 3, and we know that will cancel out. Yeah, so that's why I've got x cubed y2. Now you want to remove the 2, same thing. Divide it. Or in your case, you can think of it as squaring. But all I'm doing is I'm saying, all right, I'm going to do this to the power of half, do this to the power of half, because this is the same thing as saying y to the power of 2 times half, which again, cancels out. Which is why I know that gives you square root of x cubed. But remember, when you square it, you've got a plus and a minus. But since you know that the domain is r plus union 0, that means the range has to be r plus union 0. Therefore, you know it's the positive and not the negative graph. Okay? And so I've got my function. I've defined the domain. Okay? And so now I can just answer and just say it is, therefore, strictly increasing. Okay? Now that you know it's strictly increasing, which technically it looks like that, just a symmetry to your other graph, or you can think of it as square root of x cubed. It's just a square root function. Yeah, that's how you know. Now, I want you to look at, or if this is confusing, I want you to see it as x to the power of 3 to the power of half, which is the same thing as x. Yeah? And you remember in the power function, I told you if the numerator is larger than denominator, it curves towards your y-axis, which is why my graph looks kind of like that. As opposed to your natural square root function, your normal square root function looks like this. But then I said once you pass that y equals 1 line, where it's x to the power of 2 and 2, then it starts curving towards y-axis, which is why x to the power of 3 and 2 is going towards the y-axis. And then if you have x to the power of 4 on 2, it's quadratic. That's why it looks like a quadratic. Okay, it goes towards your y-axis. So that's my graph. I've drawn it. Now I want you to have a go, without looking at the solutions in your exercise book or textbook. Have a go with this one. Oh, is that the right one? How can they look the same? Are they the same? Oh, there's a negative. Oh, well, that's too easy then. I just don't know the answer. I thought it was something a bit more tricky. All right, don't worry about that. All right, now I'm going to put some exam questions up. Have a go with these. They're all functions. And, oh, wait, can I actually put it up? I need a download from OneDrive.